right, page 109 in your textbooks. You did problem 10 and problem 11. Kendall, we are missing you today. There is a small, no formulas available. There is a small piece of our hearts and a small piece of our classroom missing today. But no bitterness in our hearts as we think of you in the mountains right now, having a good time. Yes, and that's why we're sending you this video. Anyway, page 109, problems 10 and 11. Problem number 10. Go and read it for us if you would. Michael.
An airplane is moving at 350 kilometers per hour. If a bomb is dropped from the airplane at 1.5 kilometers, with what velocity does the bomb strike the earth? How long does it take the bomb to fall? And what is the bomb's range?
All right. Now, here's the thought. Is the bomb moving before they release it? Yes. Because it's in the plane, and the plane is moving. But the airplane, it says, is moving. We will assume, it doesn't say this, but we have to assume that airplane okay, we have to assume airplane is moving horizontally. And it says at 350 kilometers per hour. Okay, and inside the bomb bay is bomb. So it is also moving horizontally 350 kilometers per hour. And then the bomb bay opens, and they push the release mechanism, and the bomb begins to fall straight down, correct? No. It does go down, but it's still got forward movement, doesn't it? And if we're ignoring air resistance, there's nothing to slow it down horizontally. So the initial velocity of the bomb is that same 350 kilometers per hour in the x, correct? We just got a little problem with this 350 kilometers per hour. What's the issue? It's kilometers and it's hours. We don't want kilometers per hour, do we? No, heavens to Betsy. So what do? Do a little dimensional analysis, right? So we're going to change this 350 kilometers per 1 hour. We're going to multiply by a series of fractions. And Kendall, I would ask you for the first one, but you're not here. So we'll have to go to Audrey instead. 1 meter on the top? 1,000 meters in the top. There we go, okay. And that gives us meters per hour. And then Michael?
Are we trying to get meters per second?
Always.
Okay. You need to do 3,600 in the bottom seconds and 1 hour.
All right, so if we multiply that out, we get how fast is it moving in meters per second, which is a unit we can actually use. All right, so I don't even need a memory for that. That's the initial velocity in the x, correct? But there's nothing that's going to speed it up in the x, right? Once the bomb is released, it can't speed up. As long as it's in the plane, it could speed up, right? If the plane speeds up, it speeds up. Once it's released, nothing speeds it up. But if there's no air resistance, nothing slows it down either, correct? So what's the final velocity in the x?
97.2
And therefore, I'm not sure why I'm suddenly struggling with slashy marks. And then if that's the case, then that means that the average velocity in the x is 97.2 repeating meters per second. That's all in the x though. But it does drop, not straight down, but it drops as it moves forward and drops as it moves forward and drops as it moves forward. Why?
Gravity.
Gravity, absolutely. And so although initially in the y, the movement is 0 meters per second, it doesn't stay that way because it accelerates in the y at a rate of, and this is why it has to be meters per second, because we have meters per second squared here, right? So the meters, we have to have meters to work with meters, seconds to work with seconds. And eventually, this bomb is going to get faster, 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 faster until right before it hits the ground, it's going pretty fast, right? We don't know how fast. We'll say that's the final velocity in the y, and we ain't know that. Make sense? What else do I know about the vertical movement of this bomb? It's going to move, it's going to drop for 1.5 kilometers because that's the altitude at which it was. Now, technically, you say, well, what if when it hits on the top of a mountain? We're going to assume it hits at ground level, okay? Smart aleck. And so we're going to say the displacement of the y is, actually, I'm not going to say it's 1.5 kilometers. 1,500 meters. And the first thing it asks is, with what velocity does the bomb strike the Earth? Well, it strikes the Earth with this x velocity, but I don't know the y velocity, so I can't answer that question yet. Then it says, how long does it take the bomb to fall? In other words, it's looking for time. I don't know that yet either. And then it says, what is the bomb's range? What do you think they mean by what is the bomb's range? Well, the result is boom, right? Range means this. When the bombardier releases the bomb, he releases it ahead of the target, right? Because the bomb, in reality, since it's moving forward as it drops, right? It drops a little bit and then keeps moving forward and drops more, and keeps moving forward and drops more, because it's accelerating downward. The bomb is going to follow what do we call the path of the bomb? Its trajectory, right? Because the bomb, once it's released, is launched in a sense into space, can't propel itself. So the bomb here is a projectile. And we know that the path of a projectile, if you ignore air resistance, would always be what shape? Parabolic, right? In this case, half of a parabola. So the bomb release has to happen here, and the boom happens here. The nice thing is, the bombardier oftentimes has time to release bomb and turn and get out of there before bomb goes boom. Now, granted, the boom way down there shouldn't affect the plane too much, but doesn't want to get shot by the people who he is trying to go boom against, okay? So if we put it in simplistic terms. So the question is, here's where he cites to blow up something there. The range they're looking for is the displacement in the x. How far ahead of the target should he release the bomb so it goes boom in the right spot, okay? There's a terrorist outpost or terrorist bunker or something he's trying to blow up. Release the bomb, get out of there, but he's got to release it at just the right spot, or instead of blowing up terrorist bunker, he blows up like the embassy, and that's bad news, okay? So, anyway, we won't go there. All right, so that's the third thing we're looking for. You could find these in almost any order. I shouldn't say that. The displacement of the x, anyway. Which one did you choose to solve for first, Michael?
I did it wrong.
You did it wrong. Which one should we solve for first?
Probably the final velocity of the y.
Sure, why not? We can go ahead and get the final velocity in the y, and using just these variables, what would we get for the final velocity in the y? What equation should we use, I should say?
It would be f squared equals bi squared plus 2ad.
Plus
2ad.
2ad. I thought I heard 3d. I'm like, that can't be right. 2ad. I will take the square root. Once again, in the y, initial velocity 0. That's awfully nice. So 2 times the 9.8 times 1,500, we take the square root, and that bomb is moving when it hits the ground. How fast is it going? And go ahead and put that in a memory value. All right, so it's got plenty of velocity to go boom, right? It's definitely going to detonate, or almost definitely going to detonate, I should say. Back in World War II, there were times where bombs would hit in soft earth or a marsh or something and not detonate. Of course, that gave the other side a chance to diagnose the bomb and figure out what's going on, things like that. Anyway, I digress. Now that we know the final velocity of the y, remember it said, question A, with what velocity does it strike the Earth? Well, I already knew the x component. I now know the y component, so we could go ahead and get velocity and impact, right? I take the two components and I make specifically a right triangle out of them. I'm going to start with whichever is bigger, and the bigger one here is the y. So I'm going to start with 171.46, blah, 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 going downward. And then I'm going to draw the smaller vector, which is the 97.2, and that's going forward still. The resultant then will be here. Now, when we describe the angle of collision, it makes the most sense to describe the angle relative to the ground. That makes the most sense. So here's the angle we're looking for. Again, it's not the angle necessarily between the primary and the resultant, though that's normally what we would do. But here for a projectile, we'll go angle to the ground. So finding the magnitude of the resultant, how fast was the bomb going upon impact? Yeah, so 197.1 blah, blah, blah. Is it 3 sig figs in this problem or is it 2? Ooh, it's 2. That's only 1. Annoying, isn't it?
2.0 E2.
2.0 E2 meters per second. That's frustrating. 200 meters per second, basically, but we have to write it 2.0 E2. And then we need to find the angle, so let's see, that's recall 1 over the 97.22222. Take the arc tangent, and at what angle does it strike the Earth?
60.446.
So we'll say a 60-degree angle to the ground. So there's my first answer. With what velocity does it strike the Earth? That one. Questions on the first part. Second part, how long does it take? And we always use the y to find time. I would recommend go ahead and using this because I like which equation to find the time, class.
Acceleration.
I like the acceleration equation. I don't like using the displacement. So I would rather say that t equals vf minus vi over a, and just alternate the acceleration equation, remember. The v sub I is 0 anyway, so we basically just take our memory value, v sub f, and divide by the acceleration. And how long does it take to go boom? So he drops the bomb. It's not going to go boom for 17.49 seconds, right? He's got some time to make that turn and get out of there. So we'll round to 17 seconds, but that 17.496 blah, blah, blah. Make sure you put that in a memory also, because you're going to need it to find the third part, which is the range of the bomb. And how do we find range of the bomb? Or displacement in the x. Well, now none of this matters because it's all y. This could be either, and there's your other x. Yeah, the average velocity times time gives you displacement, right? V equals d over t, therefore d equals b times t. So take that average velocity of the x times the time, and how far ahead of the target should the bomb be released? Almost exactly, right? Almost exactly 1,700 meters, or you could say 1.7 kilometers if you really wanted to. But at 1.5 kilometers up, with that speed, he needs to drop it that far in advance of the target. 1.7 kilometers. Again, that's well over a mile, right? So he's well over a mile away from the target. Now, granted, you can see a plane when it's a mile away usually, okay? So they probably can see it. Could they hit it with their anti-aircraft guns? Maybe not. Not well versed enough to know that. But he at least has some time to get away before they get easy shots at him. He probably should not fly over and admire his handiwork. Anyway, questions on this? Though theoretically, again, if we're ignoring air resistance, if he did fly over, the bomb would stay directly below the plane, wouldn't it? As it was falling. So theoretically, he would be able to fly over right as it goes boom. Now, realistically, with air resistance, he would get over there a little ahead of the bomb unless he slowed down. But we're ignoring air resistance, which makes you wonder how is the plane in the air in the first place. We try not to think about those little details. All right, questions on this? Questions on this? All right, look at problem number 11 and read this for us if you would, Audrey.
Archer shoots an arrow straight up at 76.7 meters per second. A, how high does the arrow rise? B, how much time is the arrow in the air? And C, what is the arrow's velocity when it reaches the same height that it was shot from?
Now, we've actually already done this, haven't we? We did this in the last chapter. Somebody shoots an arrow to the top of like the Willis Tower, remember that? So we've actually already done problems like these. Let's go and get down, notice no horizontal movement. He shoots it straight up. So everything's vertical. We can ignore the x completely. Everything is in the y. He says he shoots it at 76.7 meters per second, class.
Initial velocity.
Initial velocity in the y. And again, if you didn't specify y, it doesn't really matter because everything's y. There is no x. And that's the only number they give us. But we know some other numbers. So we know if guy rears back and shoots it straight up, arrow goes up, and at some point will stop. Why will it come to a stop? Ever so briefly. Gravity does what? Decelerates it at a rate of
Negative 9.8
meters per second squared. And we said if it comes to a stop at the top of its flight, ever so briefly, class, we could consider that point the final velocity, which would then be 0. Now, we know it's going to make a return trip, which means its initial velocity on the return trip will be 0, and its final velocity, well, we'll get to that in a little bit. And it says, letter A, how high does the arrow rise? It's looking for displacement. What equation do we need to find displacement here, Michael?
BF squared equals, oh wait, hold up. We're going to do D. Am I changing it yet?
I guess you can. D equals
BF squared minus BI squared divided by 2A.
Okay, so you were right in what you were saying. You decided to go ahead and rearrange it already. I was actually going to go to Audrey for the rearranging after you gave me the equation, but that's okay. Which, since the VF is going to be the 0, if I'm going to say y, I might as well say it on all of them. We're going to start with the negative v sub I squared. And let's see here, that's a 76.7 squared, and then make it negative. Divided by 2 and divided by negative 9.8 gives how high, ooh, almost exact number there, how high does that arrow go?
3.147.
3 sig figs this time, I think? Yes, so we will get 300 point meters up into the air. All right, did we get that first answer?
It was really close and has 294. I'm not sure.
Maybe a typo or something. Mis-enter to 76.7 is something different. 76.1 or 76.4, your finger hit the 4 key instead of the 7 key. I know people with fat fingers have that problem. I wouldn't expect you to have that problem, but you know, it happens. Okay. Human error. All right. Anyway, there's a story there. Let's see here. Next thing we were looking for. Moving on. How much time is the arrow in the air? Well, that's pretty easy. Finding time. Well, technically, all of these numbers, class, are just for the trip up. Is the arrow only in the air on the trip up? So we've got to find time up, and then we also have time down. But again, if there's no air resistance, what's true of those two times? They'd be the same anyway. So we need to find time up, and then to get total time in the air, class, we'll simply double. What equation might we use? I'm going to put this in the memory in case I need it later. We'll overwrite that old memory one. What equation might we use to find the time on the trip upward? Audrey? The acceleration equation equals VF minus VI over T, but
you have to change it to VF minus VI over A.
there we go. And again, VF is 0, so we have a negative V sub I, so negative 76.7 divided by A, which is negative 9.8. Or you could just say, hey, I know the negatives are going to cancel anyway. And what is the time it takes to go up?
7.8.
But I need the total time, so we're going to simply multiply that by 2. And what is the total time?
15.6. 15.7.
And rounded off, it will be 15.7 seconds. There's my second answer. Third thing, what is the arrow's velocity when it reaches the same height that it was shot from? Now, I do like the way they phrase this because technically the person doesn't release the arrow directly from the ground, right? He's probably standing rearing back to shoot straight up. So there's probably a certain height to the arrow already, correct? So it's not asking for the time to return back to that starting point. But it says, what is its velocity? Well, that's asking about the return trip, right? And on the return trip, the initial velocity class is 0. The acceleration is now a positive 9.80 meters per second squared. The time in the air is going to be the same 7.82 blah, blah, blah seconds just for the return trip. The displacement is going to have to be a 300 meters. Or one might argue negative 300 meters because it's going the opposite direction of the last time. So when you go to find the final velocity in the y, since all the numbers are basically inverses of what you had before, this will be the same inverse of what you had before, negative 76.7 meters per second. And if it actually hits the archer, it's very negative. Questions on that? Questions? The math joke. Thank you for the smirk. Appreciate it. All right, the half turtle. All right, questions. Questions on this. I know, Michael, your initial thought was, I don't have anything to go off of. Does it make sense now?
Yeah.
So there's really, breaking it down, because there's 3 types of projectile problems. There's the straight up, straight down projectile problem. There's the something starts up and goes down in a half parabola. And then there's the one that we started looking at yesterday, where something starts down, goes up, and then comes back down. This, we actually did last chapter, so I don't want to spend a lot of time there, but this was a good reminder of how to work that. The airplane was one of these, like the baseball off the top of the building, like the apple being thrown to Kendall, like the arrow being shot off the top of the building, right, where it starts high and it just goes down. And then yesterday we looked at a couple of volleyball problems where something starts down, goes up, and then comes back down as well. Let's take a look at that again. So back to page 106. And let's look at our volleyball problem. And yesterday, remember, we had the girl hit the volleyball, remember, at a 30-degree angle at 20 meters per second. And the ball went high, almost high enough that if it were in our gymnasium, it might actually hit the ceiling because we have a very low ceiling. Normal gym, we should be fine. But the displacement, like, most gyms would not hold this ball, okay? It was served far enough. It's like 100 feet or something like that, remember, where most gyms are not 100 feet long, at least not from volleyball end line. I mean, maybe if she started at basketball end line to serve it, but it would still land at the other end of the gymnasium. It would still way overshoot this volleyball court. So let's change the problem here on page 106. And instead of a 30-degree angle, let's suppose we tried changing it to a 16-degree angle. We found that the ball would hit the net. And it would have worked everywhere else, but it would have just fit the length of the court, but it would have run into the net. It was too low. So maybe we're outside. Okay, outdoor volleyball for PE, where you can hit it as high as you want. We just don't want it to go out of bounds. So maybe now she hits it high up in the air. Let's make it, say, a 50-degree angle. So let's keep all the same numbers. The initial velocity is, was it 20 meters per second, right? But let's say it's launched at a 50-degree angle. And let's see what happens. The first key is to draw the vector. 50-degree angle. So here would be if she hit it straight forward, which would go under the net, but here is a 50-degree angle. 20 meters per second. Again, does she hit it upward or does she hit it forward? Yes. She hits it forward and she hits it upward. The question is, how much of the initial velocity goes forward in the x, and how much of the initial velocity is upward in the y? For this, we need to use a couple of trig ratios. We need to use sine and cosine. Which trig ratio do we use to find the x? Cosine, because it's the adjacent. So we'll say the cosine of 50, and we'll multiply that by the hypotenuse of 20. And how quickly is the ball going forward now?
13.
12.85 blah, blah, blah meters per second. Put that in the memory of your calculator. We'll overwrite memory 1 again. Memory 1 gets changed more often than baby's teething. I don't know. I wasn't sure where I was going to go with that one. Probably should have left it alone. All right. For the y, we need which trig ratio? The sine, opposite hypotenuse. We'll take the sine of 50, multiply that by 20, and how quickly does it go upward? 15.32 meters per second. Put that in memory 2. Now again, this would be a real problem hitting it this sharply upward if it were indoors. But we're going to say this is outdoors, outdoor PE or beach volleyball or something like that. So height is not a problem. You can hit it all the way up in the sky if you want to, as long as it comes down on the other team's side. All right, let's think about the x. What do I know about the x? It starts going forward at 12.85 meters per second. Then what happens to its forward movement? Nothing changes, right? If we're ignoring air resistance, nothing's going to change. So this initial velocity in the x is also the final, is also the average. It's just the velocity in the x. Okay, what do we know about the velocity in the y? What is the ball doing vertically? It's going to stop going up at some point because what goes up must come down. Newton came up with that guy. And because of gravity, which... So it starts going up in the air at 15.32, and you said it decelerates. So the acceleration of the y is negative 9.80 meters per second squared, because at some point in its parabolic trajectory, there's going to be a point where it stops rising. It's still moving, right? It's going forward still, but it's going to stop going up, because at that split-second moment, at the vertex of the parabolic glass, the final, quote-unquote, velocity in the y is 0 meters per second. The question is, how high up is that? Again, in a gym that matters. Outdoors it doesn't really matter, but I'm just curious. How high does it end up going up? How would I find this, Audrey?
Use your acceleration.
There we go, and solving for the displacement. There we go. And since the VF, again, the key is keep all the y together. Don't let any x creep in. We separate the x's and y's in all of our math. And so the VF is the 0, so we'll square the memory 2. And we'll divide by 2, and we'll divide by the negative 9.8, except the negative on the 9.8 will have canceled with this negative, so we can really just divide by 9.8. What do we get for the displacement? Almost 12 meters, right? If we were rounding to sig figs, we'd say 12 meters up in the air. In fact, I will go ahead and do that. Now, that's about 37 feet. That's a little high for a gym, but again, we're outdoors, so it's okay. The next thing I need to know is, how long is the ball actually going to stay in the air? You cannot find that directly. You must first find just like with the arrow problem on the homework, you can't find the total time in the air, but you can at least find the time up. And then double it to get total time, right? So we're going to find time up. We can use the displacement if we need to. What equation do you want to use here, Michael?
Acceleration equation.
I want to use the acceleration equation also. So I'm going to say that the A equals the VF minus PI over T. And once again, we've done this a bajillion times, Michael. To get the T by itself, alternate. We've practically almost memorized it in this form by now, haven't we? T equals VF minus VI over A. It's not a separate equation, but we've almost memorized it as if it were. The VF again is 0. The VI is that memory 2, so recall 2. Now technically it's negative, but you're going to divide it by a negative 9.8. The negatives are going to cancel anyway. How much time does it take to go up to its high point? 1.56, blah, blah, blah. I care about total time, so I'm now going to double that, multiply by 2 to get, we'll say 3.1 seconds up to the height. So it's going to go to a height of 12 meters at its highest point. It's going to stay in the air for 3.1 seconds. Now the entire time it's moving, vertically it's changing speed constantly. It slows down, slows down, slows down, slows down, slows down, speeds up, speeds up, speeds up, speeds up, speeds up. Vertically, that's what's going on. Horizontally, chugging right along, 12.85 meters per second for 3.1 seconds. So what I really wanted to know is from where she serves it to where the ball was caught. What is that range? What is the displacement in the x? Class, all I need to do is multiply the 3.126 that's on your calculator already times the recall 1. It's worse than the last time. How far is that volleyball going? I got 40.196, or approximately 41 meters, about 125 feet. No gym can hold her. She is too strong. And I mentioned this actually after the video ended yesterday, but the real problem is she's just hitting it too hard. Yes, sir?
That would be 40 meters, right?
Let's try 40 meters. Yes, thank you, sir. I was just seeing if you were paying attention. Well done. Anyway, good. 40 meters. 41. I guess my brain just ignored the 1 right here. It's like 40.96. Yes, 41. All right. Questions on this? So she needed to hit the ball softer, or as I mentioned to Audrey, it's sort of an overhand serve where the ball is already almost at net height. So it's just barely up in the air, just a very slight angle upward to get it over the net. And of course the spin is important too, though in a vacuum spin would do you no good. Spin uses the air resistance to cause the ball's flight to be affected, but I digress. Questions on this? By the way, do either of you watch baseball at all? Some baseball. You're familiar with StatCast when you're watching a baseball game. So Michael, I don't know if they do, they might even do some StatCast type stuff with soccer, but in baseball, one of the big things they like to look at is home runs. And they always talk about the launch angle, don't they? So one of the things they'll show is projected distance, miles per hour off the bat, launch angle. And launch angle is so important. The angle you're going for, again, the key to getting a home run is you got to hit it far. Well, you can hit it really hard, but if you hit it really low, it doesn't stay in the air very long. So it doesn't go over the fence usually. You want it to stay in the air as long as possible. What would give you the longest amount of time in the air? Straight up. Would maximize maximum velocity straight up, would give you greatest time in air. Well, but it didn't get the forward movement, right? So we want to maximize time in air and maximize horizontal movement at the same time. What angle do you suppose would get that?
45.
A perfect 45. So in a perfect world, your perfect launch angle for a home run would be 45. Your perfect launch angle, if you're trying to maximize distance for, say, an outfield throw, would be a 45-degree throw, right? That would give you the maximum displacement because it leaves the ball in the air as long as possible while getting as much forward movement as possible. And obviously one of the things, too, in baseball, is thinking of that with projectiles, is they sometimes talk about the ball carrying. The ball's really carrying tonight, or man, the ball's just not carrying tonight. I've seen my Cardinals play in a rather large stadium, and in St. Louis, the ball just doesn't carry. So in St. Louis, home runs don't get out very often compared to other ballparks. Well, what would cause the ball to carry? Well, we mentioned the spin. This is actually what triggered the thought is the spin of the volleyball. If you can get that spin on it, it can cause the ball to dive down. Well, if you get the opposite spin on a baseball as you're hitting it, you can get that spin and actually carry on the air. Also, if you have warm air, right? Warm air rises. So on a warm night, as the air is already having a little bit of natural rise to it, that can help to carry the ball out. Obviously, the wind blowing. If the wind's blowing out toward the outfield, that can help as well. And then other nights, cold nights, right? When the baseball season first gets started in April, you got some northern cities. Ball comes off the bat, it's not going anywhere. That colder air is more dense, creates actually more air resistance. Or sometimes in Chicago, if the wind is blowing in, and you can see the flags whipping in toward home plate, ball goes up and it just sort of dies and comes down in the outfield. And so the guy's like, man, I hit it hard enough, I should have had a homer. Yep, not in this ballpark and not tonight. Anyway, let's consider this idea of throwing the baseball. And let's suppose we're talking about a junior high JV baseball player who throws the ball, let's say 65 miles an hour. Okay, so we've got a JV baseball player. Ball's hit to him out in deep center field. He gets the ball, and he's trying to throw a runner out at home. Plays at home are always exciting to those of us who enjoy watching baseball. Do you know what home plate is?
Yeah.
At least, okay, you know home plate. Okay. So anyway, he's like totally unaffected here, soccer guy. Play at the plate is kind of like a penalty kick. You're on edge, like, what's going to happen? Is my guy going to score safely, or are we going to nab the other guy? It's like, is the keeper going to stop it, or is he just going to miss the kick, or is it going in? It's a suspense, right? It builds. You see it coming. Anyway, 65 miles an hour, and he's 300 feet deep in the outfield. Okay, so in a high school or JV park, this is pretty deep in the outfield. Major League Park, probably going 400 feet. And let's suppose when he comes up throwing, though, he throws it about like that, which means the launch angle is about a 25-degree angle. Doesn't look very good, right? He's not maximizing time in air. Now, traveling toward the plate is maximized, right? And maybe his goal is he'll play it on the bounce. It'll be a one-hopper to the plate, but I want it to get to the plate as quickly as possible, so I cut my angle down. Does that make sense? So there's a reason why he might cut the angle. Let's suppose it's a 25-degree launch angle. We do need to change these numbers a little bit for sake of staying in the SI. So let's say this is about 30 meters per second, and this is about 95 meters. This is the desired displacement in the X. But we don't actually know the displacement in the X. We know he threw the ball 30 meters per second at a 25-degree angle. So just like the volleyball player, okay, let's go ahead and calculate this out. Start by drawing the 25-degree angle and putting the 30 meters per second as being that vector. We need to find the initial and final and average forward velocity and the initial upward velocity. At your seats, find both of those components. Check your components. Did you get them right? Now, find how long the ball stays in the air. Which component do you need to find how long the ball stays in the air?
Time.
Well, time, and what component do we always use to find time? The y. We need the y to find time. What do we know about the y?
It's final velocity is 0.
At the high point of the parabola, that final velocity is going to be 0. And the time we're finding technically first is time up anyway, right? To that high point. What else do we know? Why does the final velocity go all the way down to 0?
Negative 9.8.
Acceleration of the y is negative 9.80 meters per second squared. Check your answer for time up once you've got it. We got it? But that's not how long the ball's in the air. What do we need to do to account for the ball staying in the air? Double it. So total time is... And what do we do with the total time the ball's in the air? Multiply by the velocity in the x. How far does that ball go? It's moving 27.18 meters per second toward home plate, and it keeps going for 2.587 seconds. How far does it get? 70.35 ... meters. Is that making it all the way to home plate? It's not even making it to the pitcher's mound. It's making it to about second base, making it to about to his cutoff man. So maybe a little bit past cutoff man. So it got to the infield, but that's probably a two-hopper. And every time as it hops, that encounters friction, which is going to slow the ball down. Guy probably scores. So I said this, if you want the maximum distance, if this is just as fast as he can throw a ball, biologically, the way his body is built, the way his muscles at work with the red fibers, white fibers, the way his arm length is, whatever, that's how fast he can throw a ball. Obviously you say, well, throw it faster, we'll get there. Right, but let's say that's as fast as he can throw it. We could maximize distance if we change the angle to 45. Let's find out if it is physically possible for this kid to reach home plate on that throw. If he throws it at exactly the perfect angle, what's it going to be? All right, so what's the velocity in the x now? He lost a little bit, right? By changing that launch angle to 45, it's not moving forward as quickly, is it? Put that in the new memory 1. By the way, if it's a 45, what's the velocity in the y going to be? Same thing, right? 45, 45, 90. These are going to be equal to each other, aren't they? So I already know, I don't need to waste a second memory on this. I know the initial velocity of the y is also 21.21 ... meters per second. All I need to do is change the time up and the total time. Ooh. How long does the ball take to travel up? 2.164, blah, blah, blah. So what's the total time in the air? 4.82. Notice the ball's in the air for considerably longer. So he lost a little forward velocity, but the ball's staying in the air longer, so he's going to get more distance. What do we have for his total distance? 91.83. Is he reaching home plate with that throw? The bounce maybe, but he's not getting there. And it took 4.329 seconds. Just about any baseball player can get from third to home in less than that time. So he doesn't get the guy out anyway. So pretty much, get a different outfielder who can throw it harder is pretty much what it boils down to. But do you see the math connection there? Okay. Questions on this? Questions on this? So again, as a coach, what you would look at is, okay, let me clock the kid. You get the radar gun out. Let me clock the kid's fastest throw. And you see what kid has the fastest throw. And if that's his top throw and you expect to make plays at home, now again, JV baseball, you're probably not making plays at home anyway. But if you expect to be able to make plays at home, you don't want a kid whose maximum velocity is that, right? You try to find somebody with a better velocity. Because physically, from that deep, that throw cannot make it in time. And again, the math behind it, analytics is what it's called. And I love analytics. Football has some of those as well, right? You got the Amazon AWS advanced stats or whatever they do for NFL games. Great fun. Great fun. Love numbers. All right. People used to marvel in college, like, your math education and PE. Like, nerdy math and sports. Like, I don't see how they connect. I'm like, no, you don't understand. Sports is math. Statistics, analytics, that's what sports is math. And so, yeah, it's great fun. All over, absolutely. Understand the numbers, yes. All right, anyway, I've got a handout for you, and we're not going to make it super far on the handout, but I do want to at least get started on the handout. You'll finish it for homework. I think we might have time to get the first problem done. Kendall, anyone else watching, it's in the description of the video. Yeah, let's go to a basketball court now. You notice a lot of sports connection here because I like sports. Michael's like, where's the soccer connection? I'm an American. Sorry, we will eventually get to a soccer ball. Just not on this handout. High school basketball court's 28 meters long. If a player inbounds the ball, heaving a pass 15 meters per second at 25 degrees above the horizontal, will the ball be caught inbounds or out of bounds? So I kind of think of this as the end of the game. There's 3 seconds left. You're chucking it down court to your guy. But at that speed or velocity, at that angle, where does the ball end up being caught? Inbounds or out of bounds? What should we do first? Draw a picture, absolutely. Start with the horizontal and make what appears to be a 25-degree angle. And label this vector here as this is the pass being heaved.
X. Oh, that's the 15.
That's the 15 meters per second right there. That's the 15 meters per second. Now, I need to find how much of that 15 meters per second is in the x forward and how much of it is in the initial velocity in the y upward. Check your components. If you're good, move on to the next thing, which is to find because all it asks is, does the ball stay inbounds or does it go out of bounds, right? That's all it's asking, but in order to find that, you've got to find the... No, I don't even care about the final velocity. The time. How long does the ball stay in the air? Because that's what's going to determine, the longer it stays in the air, the further it's getting, right? So I need to find the time, and in order to find time, I got to use the y component. What do I know about the y, right? And technically, you're going to find time up. And it's not up in the air very long. Or it's not going up in the air very long. Check your time up. And then, obviously, find total time. Because once you have total time, you can find how far the ball travels. Did we get the ball traveling 17.587 meters? So the question is that inbounds or out of bounds if the court's 28 meters long? That is inbounds. That ball's staying in. Okay, so that's good. Hopefully it's caught, assuming it's caught at the same height it was thrown from. Questions on that? Do we see how to handle this? Because this is the new one, the up and down. It goes up, comes back down. We could have found how high it rose, how high the ball did rise. Make sure it wouldn't hit the ceiling. It's not in the air very long. We could find the displacement upward, I suppose, but it's not going to be much. It's not hitting the ceiling, so we're fine there. We could find the velocity coming back down, but if there's no air resistance, it's going to come down at a 25-degree angle, coming down as it's being caught at 6.339, going forward at 13.59. So it's going to come back down at 15 meters per second also. So kind of like the straight up, straight down, it's going to be the same way for one of those also. All right, your homework is to finish the handout this weekend. Go and finish the handout, so problems 2 through 5. We'll take a look at this as we wrap up our section on projectiles on Monday. Have a wonderful weekend. Kendall, looking forward to seeing you back. But enjoy the time while you're gone. Bye-bye.